The real number system that we use is broken down into separate portions or separate sets. And we do this to have different kind of classifications of numbers that we're working with. The first set that we're going to be looking at is this set here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way on up. This is called the natural numbers. And they're also called the counting numbers. They're kind of like the first numbers you really would use in mathematics. And in the computer, that looks like this double bar in here. We write it with a double bar to signify the uniqueness of this set. So this is the set 1, 2, 3, on up to positive infinity. The next set is the whole numbers. Whole numbers are the ones that include 0, and the natural numbers is this W with a double bar. And so the whole number set is 0, 1, 2, 3, on up. And the final set from these numbers is this set here. And this is called the integers. It's a Z. I think Z is for Zahlen. It's a German word for number. The integers are all of the numbers that have no decimal parts, positives and negatives. That is the integers. Integers is probably one of the most important sets of numbers we use. 0, 1, 2, 3, on up to positive infinity. So it goes all the way down to negative infinity, on up to positive infinity. That's the integers. Now, of course, we do not have a portion of a whole in these, so we don't have any decimals. And that is introduced with the rational numbers. And this is designated with this Q double bar. We also use it with a Q like that. You can write it like that. This is written as a set builder. The set of A over B, such that A and B are elements of, or are just integers. So take any two integers, it doesn't matter which two, put them as a fraction over each other, and that is a rational number. If you let B equal to 1, then you end up getting back all of the integers, which means that the integers are also rational numbers. Now, I can write this as a roster method, but it's a little confusing, the pattern that you see. And the set builder is much cleaner to doing that. Now, this set is also known as a set with decimal parts that terminate or infinitely repeat. And I can actually show you that. You don't have to know this. I'm just showing you that there is an algorithm to write a number that terminates, like this one. This is a decimal that stops 0.2167 and it stops there. This is the same thing as rewriting it as an infinitely repeating decimal with zeros. Well, I can change this to a rational number by just taking the decimal portion and moving it 1, 2, 3, 4. Of course, you can't just move it. The way you rewrite that is by counting out 1, 2, 3, 4 zeros, and then in front after a 1. And so this number just goes on top without the decimal portion, and then this spaces go to the bottom. And that is an integer over an integer. They're very large, but that's still a rational number. Now, for a number that infinitely repeats, you can see here that I have an infinitely repeating portion of this 832 part. Well, the first step that we can do is move this decimal portion over, in this case, also 4 times. And that gives us this decimal portion. And then, of course, this 4 comes down here. So it's kind of like the first number I did. And then I'm going to do the side calculation here. I can take this number that has now the decimal point right before the repeating portion, and then I multiply it by how many numbers there are in the repeating portion. There is 1, 2, 3 numbers that repeat. 832, 832, 832. And I'm going to multiply it by 9, with that many numbers. So if there's 3 repeating numbers, then I'm going to multiply it by 999. If there's 4, it'd be 9999. 15, there'd be 15 nines in there. And this will always give you a integer as a result. And now all I can do is I'm just going to rewrite this statement using division. I'm just going to divide this 999 portion over. And I get this integer. That portion comes up here because all I've done is I've just multiplied both the top and bottom by 10,000 and multiplying top and bottom from this bottom fraction by 10,000. That gives me this portion here. And then you can simplify it down. It doesn't really matter. At this point, we have an integer over an integer. And once again, this process doesn't matter. You don't have to memorize this. I'm just showing you there is a process. You can take any terminating or infinitely repeating decimal portion, and you can always rewrite it into an integer over an integer. Okay, let's move on from that. Pi neither terminates, it does not stop, and it will never infinitely repeat the same thing. And by default, this cannot be written as a over b. It is not a rational number. We call this an irrational number. So the way we talk about this set is we use the declaration method because a roster is actually impossible to write. And I think we can write a set builder notation for it, but it's going to be very confusing. Whereas the declaration is much simpler. It's just numbers that have decimal part that neither terminates nor infinitely repeats. And of course, at this point, you can see, well, if we have all the numbers that have decimal part that neither terminates nor infinitely repeats, that's irrational. And then numbers that either terminate or infinitely repeat, that's rational. That's a complete divide. And if we combine these two sets together, I will say the irrational numbers is written as like this, I with a double bar. If we combine these two sets, or in the terms of set operations, we union them together, that gives us our number set that we use all the time, that you're probably used to using, the real numbers. With this R, you can also write it with a double bar R like that. And the real numbers are really great for a lot of reasons. They're nice to work with. They have great visualizations, which we'll see later on. They're just a nice set to work with. Now, because Q, the irrationals, and I, the irrationals, how they're defined is they are actually disjoint sets. And if the universe set is R, then Q complement is the irrationals, and vice versa. The irrational complement is the rationals. They are completely separate, and combining them makes up the entire rational, the entire real number system. Now I've created this diagram here. Sorry for the blurriness, but this is just a simple idea to kind of visualize the number system we have here. We have this innermost portion with n, the natural numbers. And then if we add on to n with 0, we get the whole numbers. So it's important to note that the naturals are nested inside the wholes. Every natural number is a whole number. Not every whole number, however, is a natural number. 0 is not a natural number, but it is a whole number. Think of it like every square is a rectangle, but not every rectangle is a square. That's the kind of idea we're working with here. And then if we add in these negative numbers in with 0 and the positive integers, we have the whole integer set. And then, of course, all of these are contained inside Q, as well as every other ratio of integers. And then you can see we have this complete divide here. We have the rational and irrational numbers. They're completely separated. There is no overlap. And it's important to note that this white oval here is the real numbers, not this orange box, the white oval. this orange box is actually what's called the complex numbers. And we're going to be looking at those a little bit later on. But for the most part, we're going to be working with the real numbers. Oh yeah, also it's important to note here that this is not an accurate representation. In fact, this bar should be like pushed way over here, probably. I mean, it's kind of hard to tell because we're dealing with infinite amounts of numbers. But there's actually a lot more irrational numbers than there are rational numbers. I've just drawn it this way so that there's some kind of semblance of clarity here. Okay, one thing we can do when we're talking about our number system is we can classify the numbers using these subsets, as they're called. They're all smaller portions of the real number set. And so we can ask things like, what are the sets that 15 belong into? So 15 is a natural number. Somewhere down here we have 15. But if 15 is a natural number, it must be a whole number. Therefore, it also has to be an integer. If it's an integer, it's also a rational number. And of course, it's always going to be a real number since it's contained in this white oval. So we can classify 15 using the sets. It's a natural number, a whole number, an integer, a rational, and a real. It's also a complex, but we're not dealing with that right now. We're only looking at real number subsets. Now, what set does the cube root of 3 belong into? If you were to type that onto a calculator, some really sophisticated calculator that has a lot of places, you'll see that this thing neither terminates nor infinitely repeats. So the cube root of 3 is an irrational number. If it's irrational, it is also real. So the cube root of 3 is irrational and real. It cannot be natural, whole, integer, or rational because it is irrational. That directly removes those possibilities. Okay, what set does negative 753, 2, 1, 1, 5, 1, 5, 1, 5, 1, 5, 1, 5, 1, 5, 1, 5 belong to? Well, this is an infinitely repeating decimal. That should tell you right off the bat this is a rational number. And it is. I'm not going to try and find the A over B that defines it, but it is an a rational number. I'm not going to write down, so it's going to be too long. It's going to clutter up the graph, but it cannot be an integer, right? They have no decimal part. That means that the smallest thing is, smallest in the smallest subset it's contained in, is the rationals. If it's a rational number, it must also be a real number. So it's rational and real. Finally, we have this number here, negative 45,694. This, clean up some of this stuff so that's a little bit easier to see. Negative 45694. Take a guess. Where do you think it is? It's right here. Double check that. Yeah, 694. This is an integer. A negative integer is way down here in this ... So it is not a natural. It is not whole. It's an integer. That means it's also a rational number, and it's also a real number. So what you're looking for whenever you're classifying these things is you're looking for what's the smallest subset that it fits in. Once you find that, then all you have to do is just look through all the nested subsets and then go from there. If that's not clear, then you can always go reverse. So we know it's going to be a real number because we're working with real numbers. And since negative 45694 is a decimal number, right? I can write it as negative 45694.00000. It's a terminating decimal or an infinitely repeating decimal, whichever one you want to think of it as. that means it has to be a rational number. Okay, and it has no decimal part. We can actually write it without that decimal part. So we know it has to be an integer. Now, inside the hole in the naturals, you can see that we have no negative numbers. So it cannot be a whole number or a natural number, because those do not have negatives allowed in it. Therefore, we know it stops at an integer. So that's kind of a backwards way of thinking about it. I prefer finding the smallest subset it fits in and then going backwards, but whatever makes sense to you. Give it a try in number 4.